Okay, we're continuing on here. We were talking about titrations last time. We talked about a couple of titrations, or got through one, and then started talking about the next one. We talked about a strong acid. Strong base titration, and then you guys did one in the lab. And again, in this titration, we have the base up in the burette. We're adding it to the acid. And we talked about the titration curve. With most titration curves, kind of have this sort of S sort of shape. I saw a lot of yours that you made, and they look pretty good. They have that sort of characteristic shape. But really, when you kind of break down a titration curve, there's pretty much kind of four important parts along the curve. The first part is usually the before you begin the titration. And really, in a strong acid, strong base titration, before you begin the titration, really the only thing that you have in the flask is a strong acid, which means really you could go directly into the pH equation at that point, and you can basically get your pH from that. You haven't added any volume or anything like that that you have to worry about. So whatever the strong acid concentration is, will get you the H+ concentration. You can get that pH from it. The sort of second part of a titration curve is really when you start the titration to before the equivalence point. And that's sort of the second part. And really in this type of titration, as we talked about, it does require an ice table. And really the purpose of that ice table, which should be done in moles to begin with, because we are adding volume, so the molarity is going to change. So you want to do it in a mold. The purpose really of that ice table is to figure out how the concentration of the strong acid has changed after it reacted with the base that you put in there. Because up until this point, what you're adding in terms of the strong base is going to be the limiting reagent. The excess reagent that you have plenty of will be the strong acid in this case. So you need to do that ice table really to figure out the concentration of the strong acid, how it changed. Once you've done that ice table, as we talked about in moles, it is a good practice, and you should do so to convert it back to molarity at the end of that ice table. You would use the total volume at that point, convert it to liters, and that is the amount of acid you started with, and obviously the amount of base that you added wherever you sort of stopped at that point. When we do reach the equivalence point in this type of titration, which is sort of the third part of the titration curve, at this point, and remember that the equivalence point is the point where exactly the moles of the acid will equal the moles of the base. So what you will have pretty much left over at this point is a salt. And that salt came from a strong acid and also a strong base, which means it will not go through hydrolysis, and it should be a neutral salt. So in this type of titration, we would expect the pH there at the equivalence point to be about 7, because really the only thing left over there is your salt that came from those strong acid, strong base. The fourth part of the titration curve is sort of after we go past the equivalence point. And really at that point, what's going to happen in this type of titration, as we talked about, is you're pretty much just adding base, right? So at the equivalence point, the moles of acid and base are equal to each other. Past the equivalence point, you kind of added excess amount of base. So you do need to do an ice table at this point, also should be done in moles. And the purpose of this ice table is really to figure out actually the concentration of strong base that you have left over, because at this point in the titration, all the strong acid will be gone. You'll just be dumping in pretty much base. Once you figure out the concentration of your strong base, because it is a strong base, that will get you your hydroxide concentration, which will allow you to get to the POH, and then you can get to the pH at that point. Any question on those parts there? Now, we then got into, towards the end there, another type of titration, which is a weak acid, strong base titration. And the setup here is very similar. We got our strong base up here in the burette. And once again, here we're adding it to the acid. we do get a similar looking sort of titration curve. And it has really the same sort of 4 points at the beginning here before you start the titration. In this case, though, the only thing that we have is a weak acid. So as we talked about last time, it's a little bit different in terms of getting the pH here before we begin, because the acid we're dealing with is weak, which means you do need to do pretty much a Ka type problem. So you would need to do an ice table here. Pretty much a Ka problem. And again, because we have not added any base at this point, you can do with the molarity of the acid from the beginning. You're all good to go on that. This would be the one with molarity. This would be a nice table with X's, and you would solve for X. And that X in that case will equal the H plus concentration, and that would allow you to go into the pH at that point. So a little bit different than the previous titration here because of the acid is different. It does require, again, an ice table and sort of a weak acid Ka type of problem at the start of this titration, or actually before you start titration. Now, we got up to the next part of this type of titration, which is from the start of it through to right before the equivalence point. And in this type of titration, we do need to, again, do an ice table here. This ice table, once again, should be done in moles as we're adding volume. And what you will find when you're all said and done here is you will end up with a buffer, as we talked about at the very end last time. So no matter what happens here, you would use the moles of everybody. What will be left over is a buffer. And you have really two options to get to the pH at that point. Like we talked about, you can once again do a ice table if you like with the weak acid, or you can go into the Henderson-Hasselbalch equation because it is a buffer. Again, going into the Henderson-Hasselbalch equation probably would be less room for error, I would imagine. So you can use that pH equals the pKa plus the log of the base over the acid. And again, really anywhere up through starting your titration to before the equivalent point, you will end up in sort of a buffer situation. And either two ice tables or one ice table, and the Henderson-Hasselbalch pretty much needs to be done. But again, the first ice table should be done in moles. Any questions up there? All right, so that is where we're going to pick up. So we talked about the second spot there. So let us continue on and talk about the third part of this type of titration. Once again, our weak acid, strong base titration. And we've been looking at acetic acid, which is our weak acid, and sodium hydroxide in this example, which is our strong base. Going to give us a little sodium acetate and a little H2O action. And again, just like we just talked about, we have our sodium hydroxide up in the burette, and we are adding it to our acetic acid down here in the beaker. All right, so at this point in the titration, we have reached the equivalent point. So let us talk about this part at the equivalence point. So we definitely need a reaction that I just wrote up there. And once again, we would need to do this in moles because we're obviously adding volume. So just like we were doing previously last time, I'm just going to make up some numbers. So we are starting with here, and this is what we're adding. So we're going to start with 4 moles of our acetic acid. And because we are at the equivalence point, that means the moles of sodium hydroxide should also be 4 moles, right? Because that is basically what the equivalence point means. We have exactly the same number of moles of each of those guys. We're going to zero this guy out. In this case, again, you really can't choose wrong. There's only one number, so choose that number. And the change here would be -4, -4, and +4 moles, which means at equilibrium, nothing here, and 4 moles of this guy. At this point, once we've done our initial ice table in moles, we want to convert back to molarity using the total volume. So again, we want to use our total volume here. And that would be obviously the amount of base that we added to the acid we started with, converted to liters so that everything works out correctly. At this point, if you're not sure what's going on, you can again always use your ice table to help you. And if we look at our ice table, this is pretty much the only thing we got left standing at this point, and that is a salt. And this particular salt here, will it do anything? So let's think about it here. This salt will break apart into a sodium ion and a acetate ion, right? All right. So we definitely have talked about the sodium ion a lot, right? That is group 1. That really comes from sodium hydroxide, which means it is really a neutral salt. So we know that the sodium ion is going to be neutral and really not do anything. But what about the acetate? The acetate here came from what thing? Came from acetic acid, right? Acetic acid is what type of acid? It is a weak acid, which means the acetate should be weak or strong. It should be relatively strong. And what that means is it will go through hydrolysis at this point. So unlike the previous titration at the equivalent point where we hit a salt that was pretty much neutral, in this case, we're actually going to have a salt that's going to continue to react. So what is it going to react with? It's going to react with the water that's there and go through our hydrolysis reaction. So what's going to happen here is this guy, which comes from an acid, means that this guy is really the conjugate base. So if you're not sure what's going to happen with it, it's going to act as a base when it reacts with water. And that means it's going to give away an H or accept an H if it's an acts as a base. It's going to accept the H+. So that's the important part here. So you do need to do another ice table at this point where the acetate reacts with the water. And in this case, as we talked about, the H+ is going to send itself over there. The result of that is we will make some acetic acid. By the way, it always makes where it came from, which means you always have part of the reaction done for you. Just got to put it in the right spot. Also means that we will produce a little hydroxide action here without even doing the calculation. Should we be acidic, basic, or neutral at this point? We should be basic. We're producing hydroxide. So at the equivalence point in this type of titration, we know that it should be basic because this reaction is occurring. Also, when I do the calculation, I need a what? A Ka, Kb, Kc, Kw. I need a Kb value to use here. And again, you probably will not have the Kb value in this case. You probably will have the Ka value for your weak acid. So you need to use the Kw to kind of flip it over there to the Kb value. Again, a very common mistake that people make is that they use the Ka value here. So this is going to be an ice table, and also why it's really important at this point to convert it back to molarity. You don't really want to be jumping into this table with moles. You really want to be jumping in with molarity at this point. So again, really good practice. Make sure you convert it back to molarity at the end of that first table. But that molarity that we got up there is going to be our initial here. So let's call this M1. That molarity will carry down to here. This is going to be some zeros. That's some good rain. And that's going to be minus X, plus X, and plus X. That means that when we reach equilibrium here, we'll have our initial minus X, we'll have our X and an X. This again would go into our KB expression. We would solve for X, but it is also important to remember in this case, X equals what? It equals the hydroxide concentration in this case. That's why it's really important to write the equation. Yeah, so you actually could see that and not take a 50-50 guess as to what the X will equal in this case. Yeah. So that equals the hydroxide, which means that you could get the POH from that. And once you have the POH, you could get the pH at that point. So at the equivalence point in this type of titration, very, very different than the strong acid, strong base titration, where frankly, we just lay up a 7 at that point. Here, you do need to do actually 2 ice tables. The first ice table is really to get the proper concentration of the salt that's going to be left over. At that point, the second ice table will be that salt going through hydrolysis. And because this always comes from a weak acid, that salt, you should always hit basic in this case at the equivalence point. So you will always have a salt that will go through hydrolysis and produce hydroxide. You got to make sure you got your KB value there to the OH, POH, and then to the pH. Any questions on what's happening at that point in the titration curve? Okay, so you can obviously see this titration a lot different in terms of the calculations of what is going on. So let's talk about what happens after we go past the equivalence point here, because we know we do not stop at the equivalence point anymore. So after the equivalence point, we'll call that the 4th spot. Let's talk about what will happen there. So we are still obviously having the same reaction that's occurring. So we'll do our reaction here. And once again here, this is what we're starting with. That is what we are adding. And I'm going to again use my made up starting amount of 4 moles of my acetic acid. At this point, because we are past the equivalence point, the moles of the base I'm adding should be less than, equal to, or greater than 4 in this case. So at the equivalence point, they're equal. So once you go past it, you're pretty much doing what with the base? You're just dropping it in, right? So you're adding a lot more. So because we are past the equivalence point here, we should actually have more moles of base. So I'm going to make that number up as 6 and 0. Now, past the equivalence point, there is sort of a change that occurs at this point. We have an excess amount, sort of like our excess reagent there for our sodium hydroxide. And really our acid becomes like our limiting reagent. And that means that past the equivalence point, all of the moles of the acid are going to get used up here. So that is going to be the change. And I think we just talked about it. Logically speaking, take the smaller number. Otherwise, even when you don't want to take the smaller number because you feel it's wrong, take the smaller number. Yeah. So we're going to take the acetic acid in this case as it gets used up. That's going to be a 0 there. That's going to be a couple moles left over there, maybe 4 moles left over here. And once again, we're going to be good students here and convert this back to molarity using our total volume at this point. So once again, we are left over with a couple of things here in our ice table. We have sodium acetate and we have sodium hydroxide. Are those 2 things a buffer? They are not. So although you have 2 things here and you have that other temptation of I want to use the Henderson-Hasselbalch equation, this would be incorrect. You should put a line on it yourself if you decide to do that, because that's what's going to happen. This is not a buffer. They're not related to each other. We actually have, in this case, 2 bases happening here, right? As we saw previously in the previous step, This is our salt that will go through hydrolysis and act as a base, right? And we also have sodium hydroxide, which is a strong base. Between sodium hydroxide, which is a strong base, and sodium acetate, which is not really a strong base, kind of a weaker base, which one would be probably the major contributor to the hydroxide in the solution? It would actually be the sodium hydroxide. It simply just needs to go for a swim. When it goes for a swim, it's going to produce hydroxide right off the bat. It's going to break apart into those OH minuses. The acetate, as we just saw in the previous step, it's got to go find some water, do a little reaction, right, to produce the hydroxide. So although at this point, the acetate is producing some hydroxide, its contribution to the overall OH minus in the solution is nowhere near what sodium hydroxide will be, because again, it simply just needs to go into the beaker pretty much to do it. So what we typically do past the equivalence point here is we ignore the contribution of the salt at this point, because we have that strong base that's sitting there. And because it is a strong base, that pretty much will give you your hydroxide concentration, which means you can get to your POH and then get to your pH at that point. So past the equivalence point, you do need to do one ice table in moles. Really, the purpose of that ice table is to figure out the concentration of your strong base that you have left over, and then you can get your OH minus to your POH to your pH. Once again, here, we're not going to worry about the contribution of the salt in terms of producing hydroxide. We're just going to worry about really the strong base. We don't ignore the contribution of the salt in the previous step, because frankly, it was the only thing left over at that point. So it is the major contributor in the previous step. But here, with the strong base present, it's going to be that strong base that's really going to be the major contributor. Any questions on that there? Yeah. Yeah, so in all titrations, pretty much your total volume is the volume of acid you started with in this example, plus the volume of base you added. And you usually will need to convert that probably to liters from milliliters, but yeah, you want to have them together. Any questions on that? So in this type of titration, as we just talked about, there really is those 4 distinct points, kind of before you begin, before the equivalence point, at the equivalence point. And in this situation here, the good news is it's really all calculations that we've done before. The key is to understand when to do the proper calculation. And that is why, if you understand where you are on the titration curve, you actually should know what type of problem you're doing before you even start, which makes it a lot easier than trying to figure it out as you go along. And what I mean by that, in this titration, really part 1 there is a Ka problem. Part 2 is a buffer problem. Part 3 is a hydrolysis problem. And part 4 is really just a POH type of problem at that point. So if you understand sort of where you are to begin with, it helps set you up to do the calculation. And you really should know what type of calculation you should be doing, you know, really how many ice tables you should be doing and what things you should be doing, even really before you start it. And that helps, because a lot of people second guess themselves as they just jump into the problem and go, feel like I should do this, but maybe it's right or maybe it's wrong. So, you know, it kind of helps to know, you know, where you're going before you get there, I suppose, so you can get there. All right, so let's just take a look at one here. Let's just say we did this and we let's say we had 25 milliliters of 0.1 molar acetic acid. What is the pH after we add we'll do 21.5 milliliters of 0.1 molar sodium hydroxide. Ka value for acetic acid, 1.8 times 10 to the minus 5. All right, take a few minutes. Okay, let's take a look, see how you're doing. So obviously we're going to get a reaction here that's going to occur. And that again is the same one we've been looking at, which is our acetic acid. Get it there. There we go. Plus some sodium hydroxide. Going to give us some sodium acetate, a little double displacement, and some water here. Now, obviously, this is a titration, so we are adding volume. So we do want to do everything here on the first table in moles. So we want to calculate that. So our moles of acetic acid in this case, converting our volume into liters, 0.0250 liters times the molarity here of our acid will give us our 0.0025 moles of our acid. We'll do a similar calculation there for our acetate, which would be 0.0215 liters times the molarity, 0.1 moles per liter. Again, our liters would cancel, and that would get us 0.00215 moles for our acetate. So that's going to be our, sorry, that's not sodium hydroxide. My bad. I'm sorry about that. That is sodium hydroxide. Kind of like acetate, but not really. All right. So that is obviously the moles of the sodium hydroxide there. So initially here, we would have 0.0025 moles. Our sodium hydroxide, 0.00215 moles. So this is what we're starting with. This is what we are adding, and we have 0 this guy. So the first question is, are we before, after, or at the equivalence point? So again, if we were at the equivalence point, the moles should be what, the same or different? Same. So we're not there, right? Because we have less moles of what we were adding. So we know we are actually before the equivalence point at this point, just looking at the moles here. We have less moles of sodium hydroxide means we are actually before the equivalence point here. Any questions on that? That is a good thing to think about because it should also help you understand what the change should be. The change here should be our sodium hydroxide because we're not at the equivalence point yet. So it is still the limiting reagent at this point. That means when we do reach equilibrium here, we will end up with 0.0025 minus 0.00215. Gets us 0.00035 moles. Nothing there, and 0.00215 moles at this point. So we're going to do what we should do, which is now that we've come to the conclusion here of our first ice table, we want to now convert it back to molarity. So we're going to use our total volume. And for our total volume in this case, we have started with 25 milliliters of our acid. We added 21.5 milliliters of our base. That's a grand total of 46.5 milliliters, if I'm not mistaken. So remember, we do need to convert that to liters. So we would divide each of these guys by 0.0465 liters so that we actually do convert to molarity here. And if we do that for the first guy there, going to give us 0.0465 or 0.00753 molar. And for the second guy, 0.00215 divided by 0.0465, going to get us 0.0462 molar. Any questions on the ice table here so far? So at this point, if you're not sure what is going on, you could use your ice table to help you. You got some sodium acetate and you got some acetic acid left over. Those two things are a buffer, which we should actually know from the very beginning here, because we're before the equivalence point, which means we should always end up with a buffer. So again, this is a good way to check yourself that you didn't screw up somewhere. That is a buffer. And that means that we really do have two options in this case. Once again, you could do an ice table. And if you're not sure what the ice table would look like, it would be like those common ion type ice tables where you could use the weak acid and you needed a concentration on both sides of the initial there to make sure everything works out correctly. If not, probably the Henderson-Hasselbalch is probably the easier move at this point. And that would be our pKa plus the log of our base over our acid. Our pKa value in this case going to be minus the log of the Ka, and that will give us 4.74 when you do it. So that means that the pH here will be 4.74 plus the log, and we want to make sure we get the base, which would be this guy up on top. 0.0462 divided by obviously acetic acid should still be the acid, 0.00753. So 0.0462 divided by 0.00753, take a little log action of it. Add it to 4.74, it's going to give us a pH of 5.53. Any questions on that there? So again, really at the very beginning here, once you realize two things, what type of titration it is, a weak acid, strong base, and that you're before the equivalent point, you should actually know this is where you should end up in a situation like this with a buffer. Questions? We could check how we did there, since I just like this example. That's right there between those two numbers. That's pretty good. Bad. All right. Question on this type of titration here. Okay, we're going to talk about one last type of titration curve, and it's a little bit different. We're going to talk about titration of a weak base with a strong acid. I'll spit that out, I think. That's that momentary pause for dramatic purposes. All right, so let's take a look at that one. So this is a titration of a strong acid with a weak base. Now, the orientation here is a little bit different. In this case, up in the burette is actually the strong acid. And down in the beaker is your weak base. So in this particular titration, we're actually adding acid to the base. So for example, we could do a reaction of HCl, which is a strong acid, plus some ammonia, which is a weak base. And that will give you a little ammonium chloride, which you could keep together, or if you like, you could break it apart into the two ions if you like. In this case, whichever way you want to do it. Okay, so in this titration, it is still the S sort of curve, except it's sort of upside down. And that is because initially here at the very first step, what is the only thing I have in the beaker? I have a weak base, which is why the pH actually starts high here versus low. So we're actually starting with a high pH because we're starting with a base. And as we add the acid, the pH is going to come down. And again, that's a little bit opposite of what we were looking at before. So in this case, at step number one here, before you start the titration, you have only a weak base there, which means it is basically a KB type problem. So you would take something like ammonia in this example, it would react with some water. And since it is a base, it's going to accept that and it will form NH4 plus and a little hydroxide here. Now, since you have not started the titration here, you could use molarity in this table because you haven't added any volume. So this would be a normal KB type table where you'd use the molarity of this guy. We would use some X's here. This should go into our KB expression. And obviously, we're going to solve for X. Again, it's important here to remember in this case, X is going to equal the hydroxide concentration, which will allow you to get to your POH, and then you could get to your pH at that point. So this titration, a little bit different, but kind of similar to the one we just talked about. Instead of starting with a weak acid, here we're starting with a weak base, so it will require an ice table. The purpose of that ice table is really just to figure out the concentration of your weak base at equilibrium, and also the hydroxide concentration there when it reaches equilibrium. So now we're going to actually start adding the acid in this case, and as we see on the curve, we will start to see it come down in terms of pH. And just like the other sort of titrations, the second part is pretty much the same spot. And on the second part of this titration curve, it is basically from when you start adding acid in this case to before the equivalence point. So again, here we're going to be before the equivalence point. So let's take a look at what's happening there. So at the second part, before the equivalence point, you're going to get a reaction. So our reaction here going to be our ammonia, which is our weak base in this example, our hydrochloric acid, which is our strong acid, going to, and again, it is up to you. So I'm going to separate them into ions, but if you wanted to, you could keep them together as ammonium chloride. So whatever your preference is. At this point, we do need to do this ice table in moles like all the other ones. And I'm going to use my made up number. So once again, in this case, we're actually starting with the base and we are adding the HCl or the acid. So I'm going to start with 4 moles here of my ammonia. And because I am before the equivalence point, the moles of the acid that I'm adding, should it be less than, equal to, or greater than the moles I'm starting with of base? It should be less than. Again, we're not at the equivalence point where they're equal. So once again, I'm going to make up this number of 2 and 0. So because we are before that equivalence point, we know that all of the HCl that we added is going to get used up, because at this point in the titration, the HCl is the limiting reagent, and really our ammonia here is our excess reagent. So the change part here will be -2, -2, and +2 moles. This is going to give me 2 moles of this guy, nothing of this guy, and 2 moles of this guy. Now that we've done this table here, we're going to convert it back into molarity using the total volume. And by the way, why am I ignoring this guy? Cl minus is a, what type of salt? It is a neutral salt, so might as well not put any numbers there that you might want to use along the way. So that is neutral, so you don't really need to put anything there. If you kept it together as ammonium chloride, obviously it would be there, but it's not going to really do much. So at this point in the titration, what we really have left over here is NH4 plus and NH3. Are these two guys related to each other? They are related to each other. That is a weak base and its conjugate acid, which means, again, here we have just hit a buffer in this case. So we have hit a buffer. And that means that we can go into our Henderson-Hasselbalch equation here. And that will get us our pH. You do want to watch a couple of things here. You most likely will have the Kb value here. So you want to make sure you're not using that for the pKa value. So remember that the pKa plus the pKb equals 14. So you could calculate the pKb and then subtract 14 to get to the pKa value. And that's a nice way to get there. Or you can use Kw and convert it into the Ka value and then use it as the pKa value. The third alternative is you could use the one that we talked about maybe that you might want to use or not want to use, which is you could use this version of the Henderson-Hasselbalch equation, but that does give you the pOH. So then you would need to go to the pH at that point. So you actually have three ways you could actually solve it at this point. I guess you could add a fourth way if you wanted to do an ice table as well. You could also do an ice table with the Kb for NH3 and have an initial concentration on the other side. So whichever way you do it, you will end up with a buffer at this point. It will actually be a basic buffer for most of the run there. It may dip into acidic range there towards the equivalence point. As you can see down in this range, it might dip into sort of more acidic, but most of it will be probably a basic type buffer, especially in this range. And as it starts to drop here, as we talked about, it's really not acting very much as a buffer at that point, but you will end up as a buffer. So very similar to the last type of titration, before the equivalence point, you will hit a buffer. And really the Henderson-Hasselbalch equation, you need to do one ice table to get the concentration of the components of the buffer, and then you should go into the Henderson-Hasselbalch equation. At the third point here, which is our equivalence point, let us see what is going on in this titration. At the equivalence point here, we once again will get our reaction, which is our NH3 plus our hydrochloric acid. And again, here I'm going to kind of separate them out, but if you wanted to, you could keep them together. And we will use our same starting amount here, which is 4 moles of our base, which is what we're starting with. And once again, here, this is what we're adding. So because we are at the equivalence point, we should again know that we should hit the same number of moles at this point, and that would be 0. You cannot again pick sort of the wrong number here since there is only one number. So that would be -4 all the way across there plus 4. And that gives us 0 here, 0 here, and 4 moles of this guy. Once again, here we're going to convert this back into molarity using the total volume at this point in the titration. And up at the up front here, I again can recognize that Cl- is a neutral salt, so I'm not going to worry about it. That also will help me at this point as well, because what we see we have left over is NH4 plus. Should I worry about NH4 plus doing anything? NH4 plus comes from NH3, and NH3 is a weak base, which means this would be its conjugate acid and be relatively strong in the sense that it will go through hydrolysis. So very much like the last titration, you will have a salt that will go through hydrolysis here. So you will need a second ice table here, which is the hydrolysis reaction, where it reacts with water. And again, understanding that this is really the conjugate acid will tell you what it should do. An acid should donate an H+. So it's going to send its H+ over there. And once again, in this reaction, it will always create where it came from. So you actually do have sort of the other part of the reaction for you. This will be NH3. And that is going to give me H3O plus in this case. Without doing the calculation, should I be acidic, basic, or neutral at this point? I should be acidic because, again, we do have H3O plus being formed. Also means when I do the calculation, I need a Ka value. Yeah. So again, if you see hydroxide on the product side, you should be using a Kb value. If you see H3O plus or H plus on the product side, probably Ka value is what you should be using. We are again going to carry down the final concentration to our initial spot. And this table will be done with molarity and X's. Once again, this is going to go into our Ka expression. We're going to solve for X. And from our ice table, we could see X is the H plus concentration, which means we could actually go directly into our pH at this point. So much like the previous titration at the equivalence point here, you really need two ice tables. The first ice table is to figure out the concentration of the salt you got left over. That salt will always go through hydrolysis reaction and always end up acidic at this point. And the second ice table is really just the hydrolysis reaction. Again, the key here is to make sure you use the correct K value. In this problem, you probably will be given just the Kb value for NH3. So you do need to do some conversion there. Question on the equivalence point here. All right, so as we hit the equivalence point there, this is what's going on. And then we see the same sort of, in this case, actually drop in pH. So we do see, as I scribbled all over it here, that vertical, in this case, drop as we approach the equivalence point. And that is really because as we come into the equivalence point from above, we basically blew through our buffer, so it's no longer able to handle all that acid that's being added. So we see a pretty good jump down in pH to where we reach the equivalence point where they're equal to each other. And then as we go past the equivalence point, we're again just dumping in some strong acid, which is why we see another kind of big jump past the equivalence point, and then it sort of levels out. So let's talk about the fourth spot here in our titration, and this is obviously after the equivalence point. So after the equivalence point, once again here we have our reaction we've been looking at. And again, this is what we started with. This is what we're adding using our made up number of 4 moles. Because we are again at this point past the equivalence point, we do know that the moles of what we're adding should be more than what we started with. So we'll use our 6 mole example here. That would be 0. Change would be minus 4 moles, as it does need to be the base in this case, as it becomes the living reagent. HCl, we're just dumping it in, so we got plenty of it. It's the excess reagent. Minus 4 plus 4 here. 0, 2 moles, and 4 moles of this guy. Again, we will convert back to molarity using our total volume at this point. And looking at our ice table here to see what we got going on, we have this guy here, and we have this guy here. So again, hopefully you can see that those two things, again, are not related to each other. They are not a buffer. We basically have kind of 2 acids happening here. As we saw in the previous step, our NH4 plus will go through hydrolysis. It will produce H3O plus and will be sort of acidic. But we do also have this guy here, which obviously is a strong acid. So much like what we have done before in the previous titration, although this guy here will contribute, obviously our chloride is still neutral. The NH4 plus will contribute some H3O plus. It's going to be nowhere near the amount of H plus contributed by the strong acid, because much like the strong base in the previous titration curve, all the HCl has to do is go for a swim into your beaker, and it's going to produce H plus right away, and it's a much stronger acid. So we will ignore the contribution at this point past the equivalence point of the salt, and we will look basically only at the strong acid. This again will give us our H plus concentration because it's a strong acid, and then we could go directly into our pH at this point. Question on that. So this type of titration curve and the one we just previously talked about, they really are the same sort of problems. You have just some differences in terms of what you're starting with. So you're starting with, in this case, when we look at it, a weak base. So you have a Kb problem instead of a Ka problem. Before the equivalence point, you still have a buffer problem. At the equivalence point, you have a hydrolysis problem with a salt, which in this case here of this titration will always be acidic. And past the equivalence point in this type of titration, it's really a strong acid problem. So once again, all the sort of problems and calculations here involving these titrations are ones that we've done before. The key, as I said earlier, is to understand when to kind of put it together and use the correct calculation. And just like the previous one, if you understand where you are before you start the calculation, you should have a pretty good understanding of how to do the problem. Any questions on that there? All right, why not? Let us try one of these here. Make it up, I think. Let's see. Okay, let's do so what is the pH after 27 milliliters of 0.1 molar HCl is added to 25 milliliters of 0.1 molar ammonia? We'll do Kb for ammonia is 1.8 times 10 to the minus 5. I'll give it a go. All right, take a few minutes here, see what you come up with. Okay, let's take a look since we're getting to the end here. So obviously we're going to get a reaction that's going to occur. It is the same one we've been talking about. So we'll do it here. NH3 plus some HCl, which we're adding to it. Gonna give us ammonium chloride in this case. And once again, I'm going to kind of keep them separated. If you want to keep them together, you can. So initially here, we definitely want to do it in moles. So we'll do our conversion. So taking NH3 and converting it to moles, remember to convert that to liters. So that's 0.025 times 0.1 gives us 0.0025 moles. Same thing for our HCl, 0.027 times 0.1 gives us 0.0027 moles, and 0 this guy. So this is what we're starting with in this case. This is what we're adding. Are we before, at, or after the equivalence point in this case? Once again, what we're adding, do we have more, equal to, or less moles of it? We have more moles of the HCl in this case, right? So we are definitely after the equivalence point. So in this case, we are adding the HCl, unlike the other ones where we're adding the base. So because we're past the equivalence point, remember that our base in this case will become our limiting reagent. It is a smaller number. So the change here, 0.0025, we're going to use. And plus 0.0025. That is going to zero us out here. 0.0027 minus 0.0025. Going to give us 0.0002 moles and 0.0025 moles. At this point, we do want to convert it to molarity. Our total volume is 27 milliliters we added, 25 milliliters we started with. It's like a 52, I think, yeah, 52 milliliters. So we're going to divide this by 0.052 liters, which is that milliliters converted to liters. So we do get up with molarity here. That's going to give us 0.052, 0.003846 molar, 0.0025 divided by 0.052, 0.04808 molar. At this point, we got a couple of things going on, right? Obviously, we're ignoring the chloride. At this point, what else should we ignore? We should ignore the salt since we're past the equivalence point. That means that the major contributor here to our H plus is going to be our strong acid. And because of that, that right there should be our H plus concentration, which means we could go right into the pH at this point, minus the log of 0.003846. And going to give us a pH at this point of 2.41, which is acidic, and past the equivalence point, which we would hopefully expect it probably to be that, as we're basically just dumping in at this point with some strong acid at this point. Question on that one there. Yeah. It would be just like the previous type of titration at the equivalence point. And the reason, again, at the equivalence point, it is important because frankly, that's the only thing left over at that point. So that's the only thing contributing basically to the H plus or OH minus of the solution at that point, because all the acid in the base has been used up at that point. Other questions? So see how we did here. We were somewhere in this range and we we're kind of in between. So that's good. Didn't do too bad on that one. All right. We will lay it up there for today.